Hey guys, this is Professor Janacek, and I'm going to go over implicit differentiation. So we've seen regular differentiation of an explicit function. So explicitly, a function would be something like f of x is equal to x plus 1. It's explicitly defined because I see it's using function notation. So we would say that this is in explicit form. It is quite explicit. In other words, it's directly expressed what it is. Oh, this is a function. However, something like x plus y is equal to 1, that doesn't necessarily tell me that it's a function. I don't even know if it is a function until I start doing some sort of tests on it. So we call that one the implicit form. Again, the idea is that I don't have function notation in there, and I don't necessarily know that it is function notation. I don't know what's going on with this highlighter thing. Sorry, don't know if that's going to go away. Maybe it will, maybe it won't. All right, well, continuing on. So the idea is that I don't have my function written explicitly. I don't have it f of x equals to something. I have x's and y's all kind of jumbled up together in my equation. And so that would be considered implicit form. Now, one way of working these is to simply solve for y and then differentiate explicitly. However, that's not always the case. As you can see here in the first example, we want to find dy dx for x squared plus y squared equal to 1. If we were to try to isolate the y here, we would run into problems because we would have to use the square root of both sides of the equation, and there can be some issues with that. So implicit differentiation is kind of the way to go here. Now, one thing you always have to remember, whenever you have your x's and y's all jumbled up, you will need to always remember to use the chain rule. Very, very important. So let's go ahead and take a look at that first example. First off, one thing I notice about it, just in passing, x squared plus y squared equal to 1, notice this is the unit circle. All right, but let's see, how do we differentiate that? So the idea, so let's start with our equation. X squared plus y squared is equal to 1. Then all we're going to do is take the derivative of each side with respect to x. All right, so on the left-hand side, x squared plus y squared, take the derivative of those. Again, we're taking the derivative with respect to x. So that means we'll have 2x, and then here's where my chain rule comes in. I'm going to take the derivative of x with respect to x, the derivative of x with respect to x, plus the derivative of y squared. Well, that's 2y times the derivative of, again, chain rule says the derivative of y with respect to x, that's dy dx. On the right-hand side of the equation, we have the derivative of 1 with respect to x. Well, the derivative of any constant is simply 0. So let's go ahead and simplify this bit a bit. Derivative of x with respect to x, so this bit right here, that is just a 1. So that gives us 2x plus 2y times dy dx is equal to 0. And we can solve for dy dx. Notice I'm just trying to solve for this dy dx in there. So we have 2y times dy dx is equal to 2x. So dy dx is equal to 2x over 2y. Of course, we can simplify that, and we end up with dy dx is equal to, oops, I think I left off a negative. There's a negative there. Oops. negative x over y. And there you go. That's implicit differentiation. All right, let's take a look here at example 2. We want to find y prime for sine of xy equal to x squared plus y. So since we have sine of xy is equal to x squared plus y, then we can take the derivative of each side. All right, well, the derivative of sine we know is cosine, but chain rule says I keep the inside in first, and then I'm going to multiply by the derivative of that inside. So I'm going to multiply by the derivative of x times y. But x times y, there I said it, it is a product. So we will multiply by the derivative of xy. The product rule is the derivative of the first, dx dx, times the second, plus the first times the derivative of the second. Well, derivative of y with respect to x, that's dy dx. Okay. And then we have, on the right side, the derivative of x squared is 2x, and then the chain rule says derivative of x with respect to x, plus the derivative of y with respect to x, that's dy dx. So simplifying this stuff just a wee bit, we have the cosine of xy times y plus, I'm going to go ahead and write the dy dx's as y prime. So dx dx is 1, and so dx dx is 1, dx dx is 1, y dy dx, those are I'm going to write as y prime. So we've got y plus x times y prime is equal to 2x plus y prime. Now I do need to solve for y prime, so one of the things we're going to do is we'll go ahead and distribute this cosine out. So that gives us y times the cosine of xy plus xy prime times the cosine of xy is equal to 2x plus y prime. Now I want to get all the y prime terms on one side, so we can solve for that y prime. So we've got xy prime times the cosine of xy minus y prime is equal to 2x minus y cosine of xy. Notice all I did was take this term and this term, make sure they're on the left-hand side because they both have a y prime, and then these two terms that do not have y prime, they ended up on the right-hand side. All right, so now we can factor out the y prime on the left-hand side. And finally, isolate that y prime. And there we go. All right, on to example 3 now. We want to find dy dx for y is equal to 1 over the square root of x. First thing, I'm going to go ahead and rewrite this equation as y is equal to x raised to the negative 1/2, right? A square root is a 1/2 power. However, in the denominator, that is, since it's in the denominator, it's a negative 1/2 power. Then we can take the derivative of each of these. with respect to x. Oops, that's x. So that gives us dy dx is equal to negative 1/2 times x raised to the, notice we're going to take that negative 1/2 power, subtract 1. Be careful with that. That gives us a negative 3/2. So we have a negative 3/2 power. And then, of course, the chain rule says I need to multiply by the derivative of x with respect to x. So that's dx dx, which we know is going to be 1. So dy dx is negative 1/2 x to the negative 3/2 power times 1, which we can clean up quite a bit. That's negative 1 over 2 times x to the 3/2. Notice 2 is in the denominator. That x with the negative exponent, that moves to the denominator, becomes a positive. And there we go. Dy dx. We've got it. I do want to make note of one other thing that I forgot to mention here on example 1. Notice that because I have y in the denominator, that means y cannot be equal to 0. Be careful with that. So notice what this means. Remember we said we were talking about a unit circle here? So that means that on the unit circle we have the point negative 1, 0 and positive 1, 0. At those points, dy dx does not exist. So if you're thinking of what the unit circle looks like, there's a circle, 1, negative 1. The derivative does not exist at those points. Ooh. Running out of room here. Of course, the derivative is the slope of the tangent at that, so of course the slope, the tangent line at that point would be a vertical line, and remember a vertical line has a slope that is undefined, and that's exactly what's going on there. So there you go. Enjoy.